In this brief presentation, I want to cover some of the high-level details of my literature review I recently conducted, entitled Engineering Data Privacy in the Internet of Things. I will begin by starting with the research problem and various research questions that I began with at the outset, and we'll go through some of the high-level details and interesting facts of the research, and then conclude with some final thoughts and retrospecting on the entire process. So the research problem I started with includes three primary categories. First, the Internet of Things is composed of resource-constrained devices, both computationally and electrically. These are not your big warehouse servers. These are tiny devices that are often very cheap and can be placed all over any specific physical location and then gather the data through to make smarter decisions and help consumers in whatever way possible. The second category here is that traditional data privacy models between vendors and consumers do not fit the Internet of Things landscape. So in the traditional model, maybe you're using a website and the primary interaction there is between both you and the vendor you're using. There may be some third parties involved, but generally speaking, there's sort of a control chain there. In the Internet of Things, it's much more dispersed, and you have much less control over the entire chain of devices and software being used. Therefore, in this third point here, new methodologies must be engineered to account for and tailor to the unique nature of the Internet of Things. To guide me along answering this problem, I have three research questions. So firstly, what specific and general privacy architectures exist in the Internet of Things? So there's research that can be specific to maybe smart parking or agriculture, and those proposals could be potentially generalized, as well as other research that is more general and tries to answer the question of how to design for data privacy in the entirety of the Internet of Things. Secondly, what cryptographic algorithms work within these solutions? I will try to stay away from the cryptographic methods as much as possible, but security is tightly connected with data privacy and will therefore need to cover that slightly. And finally, how does each solution incorporate, number one, implementation freedom, number two, data analyzability, and number three, device feasibility? These are the three metrics that I will be evaluating things by. Implementation freedom just briefly refers to the ability to modify code or is designed in such a way that it can be manipulated without damaging the data privacy itself, as well as the variety of applications that a particular architecture will fit. Data analyzability, of course, is can you actually derive valuable information from this particular architecture? And device feasibility, will these algorithms run on a resource-constrained device? Moving on to the rationale and purpose of this literature review. Firstly, the rationale is that the current Internet of Things situation is often disorganized and does not adequately value data privacy. And the purpose, of course, is to discover transcendent principles and feasible architectures for ensuring data privacy in the Internet of Things. So we wanted to derive a more generic solution that we can apply, or at least principles from that. So next I want to cover some of the high-level interesting facts about some of these general and specific architectures. For the general architectures, here are just a sampling of some of the things that I covered in this literature review. First, the privacy development language. This was a unique idea to have both executable and human-readable privacy rules. So your code can both derive a description for a human making a decision about how much privacy they want to have, and yet that same code can also be executable to ensure that privacy as a control access. Second, object security architecture, also known as OSCAR. This is a proposal that includes it's an extension of the Constrained Application Protocol extension that is built for the Internet of Things with a modified datagram transport layer security system to create a trust network that doesn't compromise on energy and memory limitations of these resource-constrained devices. So it's an extension of a popular protocol, and does a good job of creating trust through that whole system and thereby ensuring data privacy. My personal favorite is Privacy Preserving Aggregation Protocol. In this research, the authors suggest a system of master, sync, and general nodes, so a three-tiered system using partial homomorphic encryption, which allows you to add encrypted values and yet have a decrypted result of the sum of them. And this proposal here also incorporates anonymity for what they call correlatable aggregation, which is essentially not just creating valuable information from it, but also being able to correlate that with certain sections. Secondly, moving on to specific architectures, here are some 4 categories that I've covered: smart grids, smart parking, agriculture, and digital health. So the smart grids proposal, there's a number of research articles on that. They include different types of encryption, fully homomorphic or partial homomorphic encryption. The difference between those two is essentially partial allows you to do addition of the encryption values for a decrypted sum, and fully homomorphic means that you can both add and multiply values to get a decrypted result. As well as the more innovative differential privacy that doesn't require as much computational overhead to compute results. And then these proposals here included often a 3-tier data collection design, as stated earlier in the general proposal as well. For smart parking, the researchers were able to make some specific considerations in designing an architecture. They were able to employ a zero-knowledge protocol that doesn't reveal any personally identifiable information, not even location, not name, not identifiers that could be necessarily later associated with that user. And it's done in such a way that you could have a completely open transmission line between, for example, the smart parking meter and the user trying to determine whether they can actually go and have permission to park in that zone, as an example. For agriculture, it's sort of a different situation. There's sort of existing systems, and so some of the research proposes access control by regulation through a connected system of systems. And digital health, there's also some unique considerations there. Some of the proposals included a smartphone hub of these wireless body area networks, but have the additional restriction of needing to have minimal electromagnetic interference, for example, for patients that have pacemakers or other things that could be interfered by. So some of the knowledge contributions, I want to cover just four aspects of this as sort of conclusions from the literature review. So firstly, most encryption methods are simply too heavy. So the traditional concept of using asymmetric encryption, for example, that laptops and desktops and even some smartphones employ, is simply not feasible for resource-constrained devices. So other techniques such as homomorphic encryption and elliptic curve cryptography are more feasible. But there's also some new concepts such as differential privacy that may be able to address some of these concerns by drastically reducing that overhead. Secondly, creativity within the specific domain often allows for better solutions. So as I've seen in the smart parking example, a zero-knowledge proof algorithm could be employed to not just protect the data, but also allow for a completely open transmission line where you could have an eavesdropper and you're not going to actually get any information, even if you decrypt the values that are being sent back and forth. You won't be able to prove that you have, for example, the privilege to park at a particular spot. Third, many Internet of Things proposals do not respect user privacy. So meeting the 3 metrics that I've prescribed above of implementation freedom, data analyzability, and device feasibility is rare among current research. More research is needed in this area to be able to come up with adequate proposals and the adequate body of knowledge to apply these in a satisfactory manner. And finally, multi-tiered networks provide the best overall architecture for data privacy. So as seen in many of these sources, having intermediary aggregation devices works pretty well for protecting privacy and encouraging well-formed security implementations. For example, in the smart metering research that I analyzed, there was multiple suggestions of the three tiers of a single the single house level meters, and then a intermediary aggregate device, and then having the collector at the top level that power companies and other interested parties could access. And so finally here, I want to cover just a quick retrospective of this process of literature review, as it is my first. So number one, research often and early. Critically evaluating and synthesizing research is both time-consuming and mentally exhausting. I had plenty of nights where I was pouring through research articles and critically evaluating them, and it was just exhausting. So doing it more often and earlier would be better. Second, making an extensive annotated bibliography. Even though this was a dedicated assignment, that was extremely helpful. Even after I organized citations and abstractions in a particular piece of software, I heavily referenced my own thoughts on each piece while drafting. So, referring back to the bibliography pretty frequently. Number three, at least for myself, do not be afraid to disagree with researchers. Nearly every research article I was reading, claims to be the best solution compared to its predecessors, and it can be sort of daunting to say, well, they have more understanding of this topic than I do, so how can I disagree with them? But sort of getting the broader perspective while reading multiple pieces. And number four, look for the common principles in the literature. So I was very focused on evaluating and critically evaluating the different literature pieces, but I think it's important to early on start looking for those common principles between the articles, especially for a literature review when you really have to synthesize your own view on it. So only after reading quite a few different articles did I start to realize some of those principles. So to conclude, here are some of the key sources that I used. I have many others, but these are sort of the top three. The first I already mentioned as perhaps my favorite, the Privacy Preserving Aggregation Protocol for the Internet of Things. Also, this article by Molina covers a bunch of different cryptographic approaches and how feasible they are on different resource-constrained devices. And then finally, this article, the original article on OSCAR, the Object Security Architecture for the Internet of Things. So I hope at this point you have hopefully learned something, and I have at least piqued your interest in the subject. Please check out the actual literature review itself if you're interested for more, and thank you for your time.